Okay, hello again. So this is the first lecture in a two-parter on stellar evolution, how stars change over time. So the thing about stars is that how they end their lives is entirely dependent on their mass. Low mass stars have a different result than high mass stars. So I've divided our stellar evolution lectures into two parts, the evolution of low mass stars and the evolution of high mass stars. And so we will start now with the evolution of low mass stars. But before we do that, let's remind ourselves what goes on in the interior of stars while they are on the main sequence. So this diagonal line right here. So we talked about this in some detail when we talked about the sun. So stars are big balls of plasma that are in hydrostatic equilibrium. So gravity is always working to pull a star kind of in on itself. The reason it doesn't succeed is because of the fusion of hydrogen in the stellar core. This fusion creates heat, and that hot gas pushes outward. So this outward thermal pressure balances the inward gravitational force to create a stable ball that we call a star. And we say the star is in hydrostatic equilibrium. So this is just a simple diagram of what is happening. So we have gravity pushing in, the heat from fusion creating a pressure that is pushing out, creating this basically a stable, mostly a sphere. So this hydrogen fusion will last a long time. A star the size of our sun, we think will keep on with that for about 10 billion years. And stars that are less massive will go on for longer. But eventually, the hydrogen will run out. So what happens then? So as I mentioned at the beginning, exactly what happens depends on the mass of the star, and we're going to focus on low mass stars for now. Low mass in this case means about 8 times the mass of the sun or 8 solar masses or less. Okay, so we have a star on the main sequence. This is a representation of the HR diagram, luminosity up here, temperature down here, the main sequence, this black line. So we have a star on the main sequence that is less than 8 solar masses. So it's fusing hydrogen in its core until one day the hydrogen runs out. All the hydrogen has been converted into helium. At this point, the core temperature is about 15 million Kelvin, which is hot enough for hydrogen fusion, but not for helium fusion. So as you go kind of outward from the center of the star, the temperatures just decrease. They just get cooler. So it's not hot enough for really even hydrogen to fuse. So suddenly there's no source of energy to keep the star propped up against gravity, and gravity starts to win. So the star slowly starts to collapse, but this collapse in turn heats up the core. So at this point, the star is moving off the main sequence and into the red giant phase. So you have a star here, low mass star on the main sequence. It is starting to move this direction to become a red giant. All right, so we have a core of helium that is contracting and heating up, and a shell of hydrogen around the helium core that heats up enough actually to start fusion again. So this produces a lot of heat and radiation pressure to push outward, and the star will actually expand. As the outer layers of the star expand outward, they cool down, making the surface temperature of the star lower and appear red. So the star expands by a lot. The final radius at this stage is 10 to 100 times what it was as a main sequence star, but the surface temperature is about half of what it used to be. So even so, the luminosity increases because of the star's new gigantic size. And so this star is now a red giant, and it will spend a couple billion years in this phase. So this is just a cartoon of what's going on. We have a helium core that's not really fusing anything, but a hydrogen shell that has become hot enough to fuse, which is producing heat that's expanding the outer layers and puffing the star up. So we have the low mass star. We are now firmly a red giant. We've moved along this track to this area of the HR diagram. Okay, so flash forward a couple billion years, and the star is ready to enter a new phase. So the core will continue to heat up until it's hot enough to fuse helium. When this starts, it's actually called the helium flash, where a huge amount of helium fuses into carbon in just a few seconds. So this flash doesn't last very long, really just a few seconds. And after that, helium fuses at kind of a slower and more stable rate. After the helium flash, the luminosity of the star decreases and the outer layers of the star kind of fall back a little bit. So the star shrinks a little bit. So now it is a horizontal branch star. So we've gone from the main sequence up to being a red giant. Helium flash occurs, and now the star is down here in the horizontal branch. So this helium fusion leaves behind carbon. And over time, right, this carbon collects in the core of the star. Eventually, we have a carbon core. So a helium shell then forms around that carbon core, and a hydrogen shell forms around that. So we're starting to get kind of concentric shells. The core isn't hot enough to fuse carbon, but it's usually hot enough to maybe form some oxygen. So eventually we'll end up with kind of a mostly carbon, but some oxygen core. In the helium shell, helium fuses into carbon, and in the hydrogen shell, the hydrogen fuses into helium. So that's what we have kind of illustrated here. We have this carbon core, we have a shell of helium that is fusing, and a shell of hydrogen that is fusing. So this, this burning, these nuclear reactions causes the star to expand again, becoming even redder. So this is the beginning of a second red giant phase, or sometimes called the asymptotic giant branch, or AGB phase. So we see here we have the star main sequence going up to be a red giant, down helium core, helium burning core between the horizontal branch, and then we go back up to the asymptotic giant branch right up here. So the core is never going to be hot enough to fuse carbon, but the helium shell will undergo fusion in a series of flashes that will cause pulsations that push the outer layers outward. The star at this point is really huge, so it will have very little surface gravity. So during these pulsations, the outer layers of gas will get pushed out and escape from the star. And so that is what is illustrated in this plot right here. It's a plot of the luminosity for a sun-like star over time. So it shows, kind of leaves the main sequence, how much brighter it gets just before the helium flash, its subsequent shrinking, and then the pulsations in brightness that eject the outer layers kind of in phases, right? The final stage is the ejection of the hydrogen and helium layers. So these layers are still hot, and they will glow to form something called a planetary nebula. So here is a planetary nebula. It's the Ring Nebula. At the center is a remnant star called a white dwarf. So not all planetary nebula look like this. They kind of can come in several different types of shapes. It kind of in some ways depends on our orientation to them, how we see them. But in the middle of all of them is a white dwarf star. So this is the carbon oxygen core of that progenitor star, of that original star. It is not held up by fusion. So instead, it's held up against gravity by something called electron degeneracy pressure. You can think about it kind of like this, like you have these atoms, some atomic nuclei surrounded by an electron cloud. So electrons can't inhabit the same space at the same time. So electron degeneracy pressure is this outward pressure caused by squeezing the atoms so their electron clouds basically can't get any closer to each other. White dwarf stars will have a surface temperature initially of around 200,000 Kelvin, which is why they are kind of on the left side of the HR diagram, right? We've gone from the main sequence through the red giant phase, down to the horizontal branch, up into the asymptotic giant branch, ejects all the outer layers, becomes a planetary nebula, and kind of sweeps down right here to be a white dwarf. Um, Over time, they will cool down and they will become redder and even less luminous than they are then. So these stars are very dense. A white dwarf, the mass of the sun, will be about the same size as the Earth, right? So really dense, but not the most dense material we will talk about in this series of lectures. There's a limit to how massive a white dwarf can be, and it's 1.4 solar masses, also called the Chandrasekhar limit. So the final form of a low mass star is a white dwarf. This is not true for stars more than 8 times the mass of the sun. Those stars have a different fate, which we will talk about in the next lecture.